Question 1. This question is about the photoelectric effect. So the photoelectric effect, we are basically using these formulas over here, which will be explained as we go through this question. So the diagram shows a setup of an experiment designed to verify Einstein's model of the photoelectric effect. So we have light shining in here. Now the photoelectric effect basically says that when light shines on a metal surface, there can be an emission of electrons. Electrons can actually jump off, and those electrons can be given certain amounts of energy according to this formula over here, that E, the energy of a photon, is equal to Planck's constant times the frequency of that photon. Einstein gave the thought that light can be viewed as particles, and each particle we call a photon, and the energy of each photon is given by that formula over here. So you have E is coming in there. That energy is used for the electron to escape. And then if there's any extra energy left over, it's given as kinetic energy. So the electron will therefore move at a certain speed. So we have here that explain how the maximum kinetic energy of the electrons ejected from the positive electrode is determined. So what actually happens here is that these electrons, as they jump off, are given, they have to take off a certain amount of energy. Now the minimum amount of energy to jump off here is called the work function. See that we're given that, and that's the work function, and that's the minimum amount of energy that is needed to eject an electron from a metal surface. Now if we just have the work function, that's in other words a minimum amount of energy to release, it means that it will have a maximum amount of energy for kinetic energy. Now what we do here with this is that we adjust the potential difference. You adjust the V, the potential difference, the PD, to the point where no current flows. So when your ammeter, when this reads 0 amps, so that there is no charge, because what actually happens is that this electron jumps off and it travels across over here and it forms a current, and then you get a current flowing, a flow of charge. Now because this over here is positive and this over here is negative, as you adjust this voltage, you make this difference here, this negative and positive, greater, and so the electron actually starts to go across but slows down and then never quite reaches there, but it heads back again after a while. So we're at the voltage where the kinetic energy is being stopped by the potential, by the voltage, by that energy. That is when you have got your, that will give an idea of the maximum kinetic energy. So you adjust the V, the potential difference, to the point where no current flows, and then what you can do from there, when your ammeter is reading 0 and the kinetic energy, the EK, is going to equal EV. That is your energy that is given due to the potential difference. Now we have here this diagram. It says light of frequency F is shone onto a tungsten electrode in A. The potential Vs, for which the photoelectric current is 0, is recorded for the different values of F. So we have different frequencies and we have our Vs. Now we're actually going to be using this formula over here, that HF is equal to HF0 plus EV. Now So state the Einstein photoelectric equation in the form of Vs and F. Define, other than the electric charge, any other symbols that you may use. So we've got this over here. This over here would be your Vs over there. So the other things that we've got here that we need to state is we've got H, which is Planck's constant. Planck's constant. We have our F0, which is what we call our threshold frequency. And that is a frequency that below this frequency, no electrons are emitted. So at F0 is when you have, it's just enough energy to be able to eject an electron from a surface metal. Now, the HF0 here, this HF0 equals phi, the energy, that's the minimum amount of energy to eject an electron, the work function. And then you have, and any other symbols, so we've got that. We could define, we've got actually everything we need, but just to define this one also in case you use that over here. This over here, phi, is your work function, and that's your minimum energy required to emit an electron. Okay, so that would be your 3 marks there. Now, we're just going to go over the page, but we'll come back to this now just to read the next question. It says, outline how a graph Vs against F can be used to find the Planck's constant and the work function of tungsten. So let's just go back here. We actually needed to draw, I missed out this question over here, using the axis below, sketch a graph of how it would be Vs to vary with F. Now your graph would look something like this. There's a straight line. It stops here because this is your V stopping. This over here would be your F0. This is the minimum amount, the smallest amount, smallest frequency in which the photoelectric occurs. But at that point, there is no kinetic energy. The electrons have no kinetic energy, so your Vs is still equal to 0. Now, we have to think of this graph in relationship to this formula over here. That HF is equal to HF0 plus EV. Now I'm going to change this formula around because we have got our V here. So we're going to have EV is equal to HF minus HF0. Or V is equal to H over EF minus HF0 over E. So we want to work out 2 things. We want to work out our Planck's constant, and we also want to work out the work function. Now if you look at this equation here and you think of y is equal to mx plus c, what one can see here is that the m, the slope of the graph, is equal to h over e. So you work out the Planck's constant, the slope of the graph is equal to h over e. Therefore, h is equal to e times the slope of the graph, where e is your elementary charge. E minus is equal to 1.6 times 10 to the negative 19 coulombs. Okay, so that's how you work out h. Now, to work out your work function is actually, if I project this down, this over here would equal that. Now, as we said before, HF0 is equal to phi. So your C would equal HF0 over E, like that. That is your y-intercept, and we don't worry about the negative or positive because we are looking at energy, which is not a vector, so we're not worried about the positive, negative. So we can replace this HF0 by your phi there. So phi, the work function, is equal to the y-intercept times by E. So to find you find that's equal to the y-intercept, all right, or your, in this case, your VS intercept times by E. Now going back over the page to this question, we have the work function of tungsten is 4.5 eV. Show that the de Broglie wavelength of an electron that has this energy is about 0.6 nanometers. Now, the de Broglie wavelength comes from this over here, that P is equal to H over lambda. That's the formula to work out the de Broglie wavelength. This P here is your momentum. Now we know that momentum, P, is equal to mv. But in looking at that, we don't use that formula, although we use that in a way. From this over here, this 4.5 eV, that is an energy. That is an energy value. So that energy would be in kinetic energy. So we have your EK is equal to a half mv squared. Now I'm going to change this formula around and say EK is equal to m squared v squared over 2m. I hope you can see that this is the same as that. I've just changed it around. I've just multiplied top and bottom by m, and I've brought my half and I've divided by 2. It's the same thing. But this m squared v squared is equal to p squared. So I've got p squared over 2m. So I can say that p squared is equal to 2m EK, and with that, if I take that, I can get rid of my that, and I've got my p. Therefore, if I go over here, I've got lambda is equal to h over p. So I'm going to get my h over 2m EK. But my EK is given by this 4.5 eV, because that's the energy, and the energy will be in its kinetic energy. But I'd have to change that EV into joules, and the way that you change an EV into joules is you multiply by 1.6 times 10 to the negative 19 to get it into joules. So that would be your conversion factor. So I'm going to get my lambda is equal to h, which is equal to 6.6 times 10 to the negative 34, divided by the square root. I'll make a long square root there. We're going to get 2 times the mass of an electron. Here, mass of electron is 9.1 times 10 to the negative 31 kilograms, times my EK, which is 4.5 eV, but I've got to change it into joules. So I multiply that by 1.6 times 10 to the negative 19. So we've got all of that. And please make sure that you do this, when you do all of this, that you use your brackets and you don't make any mistakes on your calculator, because you get an answer here of 5.765 times 10 to the negative 10 meters, which is about 6 times 10 to the negative 10 meters, which is about 0.6 nano, and nano is 10 to the minus 9, and nano is equal to 10 to the minus 9, so nanometers.